In today's lecture, we shall be discussing methods of preparation of alkyl halides by addition of halogen acids to alkenes and by substitution of alcohols. Monohalides can be prepared by electrophilic addition of halogen acids, that is HBr, HCl and Hi to an alkene. These reactions can be carried out in various solvents like pentane, benzene, dichloromethane, chloroform and acetic acid. The order of reactivity of halogen acids is Hi greater than HBr greater than HCl and HF is not reactive. This order of reactivity can be explained on the basis of bond dissociation energies of halogen acids. That is, the bond dissociation energy of Hi is lowest, which is 300 kilojoules per mole, followed by HBr, which is 365 kilojoules per mole, and HCl, which is 430 kilojoules per mole. That means that Hi can donate its proton very easily. Hence, Hi is most reactive halogen acid when we talk of electrophilic addition reactions, since H plus is a strong electrophile. Here I have shown a simple reaction of HBr to a symmetrical alkene. What is a symmetrical alkene? A symmetrical alkene is the one in which the carbons containing the double bonds are attached to the identical groups. That means that in this case, both the carbons are attached to one group, which is an ethyl, and the second group, which is a hydrogen. So they are equally substituted. In such a case, when we carry out the reaction with HBr, the Br or the H can go or can add to either of the carbon atoms, resulting in the formation of 3-bromohexane, and the yield is 76%. Reaction is carried out in presence of chloroform at minus 30 degrees Celsius. If we look into the general mechanism, or how do we explain this electrophilic addition, then we say that this reaction is an example of electrophilic addition reaction because the reaction is triggered by the attack of a strong electrophile, which is a proton, on the pi electrons of the carbon-carbon double bond. In this case, the double bond of alkenes acts as a nucleophile and it transfers its 2 pi electrons to the electrophilic species, which in this case is a proton. This helps in generating a carbocation, which is a reactive intermediate. This concept I have again explained with the help of this slide, in which we can say that the sigma bond between two carbon atoms is strong, whereas the pi bond is weak, since in these bonds the pi electrons are loosely held to the nucleus of the carbon atoms. So these pi electrons can now act as nucleophiles and proton is acting as an electrophile. And a bond is formed between one of the carbon atoms and the electrophile, resulting in the formation of carbocation, in which carbon has a positive charge on it, and this carbon, which is bearing the positive charge, is sp2 hybridized, and it has an empty p orbital with which the Br minus or whichever halide we are taking will form a bond, resulting in the formation of product. So the mechanism, if we look into the reaction mechanism, what we find is the mechanism is ionic in nature. That is, the first step will involve the protonation of the carbon double bond, resulting in the formation of a carbocation. So in this case, the pi electrons acting as a nucleophile will make a bond with the proton, which is here acting as an electrophile, resulting in the formation of a carbocation. Now in the second step, the carbocation will form a bond with the bromide ion, resulting in formation of 2-bromobutane. In this case, we had started the reaction with 2-butene and HBr. And what we've observed is that HBr has added to the two ends of the carbon-carbon double bond. Now, if we talk of addition of HBr to unsymmetrical alkenes, then the reaction is little different. What is an unsymmetrical alkene? An unsymmetrical alkene is the one in which the two carbon atoms containing the double bond are attached to different groups. In this slide, again, you can see that one of the carbons is attached to an alkyl group and a hydrogen atom, whereas the second is bonded to hydrogens. That means that this alkene is unsymmetrical. Now, what do we observe in this case? That when we carry out the reaction with HX, X is going to that carbon which is having less number of hydrogens. That is, X is adding to a carbon which is attached to one hydrogen and one alkyl group, and not to that carbon which is bonded to two hydrogen atoms. Similarly, if we look into the second example, what we find that in this case, one carbon is attached to alkyl groups and the other carbon is attached to two hydrogens. That means one of the carbon is highly alkylated. Again, in this case, we observe that the halogen is adding to that carbon which is more highly substituted. In third case, we've taken a carbon in which it is attached to two alkyl groups, and the second carbon containing the double bond is attached to a hydrogen and to an alkyl group. In this case, again, the negative part of the reagent, that is halogen, is adding to that carbon which is more highly alkylated. So this was explained by Markovnikov's, and he said that when we are adding an unsymmetrical reagent, that is HBr, to an unsymmetrical alkene, he observed that proton will add to less substituted carbon atom of the double bond of an unsymmetrical alkene. That means the reaction is regioselective in each case, because one of the two possible orientations of additions products is formed preferentially. That is, if I talk of propene, then what we find is that in case of propene, if we carry out the reaction with HBr, we will exclusively get 2 bromopropane instead of 1 bromopropane. So in practice, we can say this addition reaction is so highly regioselective that it can be considered to be regiospecific. Markovnikov simplified this rule in 1870 in a simple statement. He said that when an unsymmetrically substituted alkene reacts with a hydrogen halide, the hydrogen adds to the carbon that has greater number of hydrogen substituents, and the halogen adds to the carbon which is having fewer hydrogen substituents. In other words, halogen will add to that carbon which is more highly alkylated, or halogen will add to that carbon which is having less number of hydrogens. So now let us look into few more examples. That if we look into the example of 2-methyl-2-butene with HBr, then what is observed that 2-methyl-2-bromo, that is 2-bromo, 2-methyl-butane is the major product and not 2-bromo-3-methyl. So what is the mechanism of this reaction? In the first step, the double bond will act as a nucleophile and it will form a bond with the proton. Now, when there are two possibilities, that this proton can either add to a carbon which is attached to 2 methyl groups, or it can attach to a carbon which is attached to 1 hydrogen and 1 methyl. So what we find here is that if hydrogen adds to that carbon which is less alkylated, then it results in the formation of a tertiary carbocation. Whereas if hydrogen adds to a carbon which is more highly alkylated, then a secondary carbocation is formed. And we know that tertiary carbocations are more stable as compared to a secondary carbocation. Hence, the tendency will be the formation of tertiary carbocation. Since the tertiary carbocation is more stable, this reaction will also be favored kinetically, since the energy of the tertiary carbocation is lower as compared to a secondary carbocation. And the 2 methyl groups which are attached to a tertiary carbocation, to a tertiary carbon, they will also stabilize this carbocation through plus I effect and through hyperconjugative effect, as a result of which the positive charge is delocalized. Hence, this pathway is the favored pathway. Now, in the second step, the bromide ion will form a bond with the carbon which has a positive charge on it. Now, so that means that the reaction is proceeding along that path which will give rise to more stable carbocation, and hence now the Markovnikov's rule can be extended, and it can be said that in an electrophilic addition to an alkene, the electrophile adds in such a way so to generate a more stable intermediate, which in this case is a carbocation. Here again I have shown an example of cyclohexene, 1-methyl-1-cyclohexene, in which the reaction is being carried out with HBr. Again, we've depicted the two carbocations which can be formed in course of the reaction. And what we find is that the tertiary carbocation, in which the carbon bearing the methyl group has a positive charge, is more stable as compared to the intermediate, in which the carbon which is not alkylated is bearing a positive charge. In first case, the carbocation is tertiary, whereas the second case, the carbocation is secondary. So what we find is we get the product which is 2-bromo, 2-methyl cyclohexane, rather than the product 1-bromo, 2-methyl cyclohexane. So we can now again conclude that electrophile adds to the less substituted end of the double bond and which gives rise to a more stable carbocation. Not only HCl, not only HBr, HI and HCl can also add across the double bond according to Markovnikov's rule. And in the first example, I have shown taken an example of methylene cyclohexane, and in this case again HI is adding across the double bond according to Markovnikov rule, giving rise to 1-iodo-1-methyl cyclohexane. In second case, we've added HCl to 2-methyl-2-pentene, and in this case again the product is 2-chloro-2-methyl-pentane according to Markovnikov's rule. Now that the carbocations are formed as intermediates in electrophilic substitution reactions can also be proved by the fact that in some reactions carbocations undergo rearrangements when halogen halides are added to alkenes. So what we find is, how do they undergo rearrangement? They show Wagner-Meerwein rearrangement or rearrangements in which hydrogen, alkyl or aryl groups migrates from one carbon to a neighbouring carbon, and these shifts are also known as 1,2 shifts. That is, in this case, a carbocation which is first formed will rearrange, if there is a possibility, into a more stable carbocation by an hydride shift, methyl shift or an aryl shift, giving rise to a more stable carbocation, which in the second step will then react with an halide to give us a product. So here what I have shown, that if we do the reaction of 3-methyl-1-butene with HCl, then what we find is that the reaction is no more regioselective. Rather, we get two products, 2-chloro-3-methyl-butane, which is formed in 40% yield, and 2-chloro-2-methyl-butane, which is formed in 60% yield. So what we find is, in this case, the addition begins in the usual way, by which the protonation of the double bond takes place, giving rise to a secondary carbocation. This is the first intermediate. Now, as I've shown, the secondary carbocation undergoes hydride shift to give a tertiary carbocation. Since tertiary carbocation is more stable than a secondary carbocation, and this tertiary carbocation then reacts with HCl to give us 2-chloro-2-methyl-butane in 60% yield and 2-chloro-3-methyl-butane in 40% yield, and 2-chloro-2-methyl-butane in 60% yield. How can we explain the reaction? In this case, the secondary carbocation formed as a first intermediate undergoes hydride shift to form more stable carbocation, which is tertiary carbocation, and this results in the formation of two products. Similarly, we can take another example in which we carry out the reaction of 3,3-dimethyl-1-butene with HBr. And the major product formed in this reaction is 2-bromo-2,3-dimethylbutane. So how do we explain this reaction? If we presume that there was no rearrangement in the reaction, then the product would have been 2-bromo-3,3-dimethylbutane, which is not the case. So let us look into the explanation of the reaction. In first case, the protonation of the alkene takes place, resulting in the formation of secondary carbocation. Now, since tertiary carbocation is more stable as compared to secondary carbocation, there is a methyl shift, that is 1,2-hydride shift, resulting in the formation of a tertiary carbocation. And this tertiary carbocation then reacts with bromide ion to form 2-bromo-3,3-dimethylbutane. Now, let us quickly summarize the electrophilic addition reactions. So what we observe is that if we are carrying out the reaction of a symmetrical alkene with a halogen acid, then the halogen acid can add on the either side of the double bond. Whereas if we are taking an unsymmetrical alkene, then in that case the negative part will go to that carbon which is less substituted. This is an example of electrophilic addition reaction. The mechanism is ionic. In my next lecture, we shall be starting with the preparation of alkyl halides by halogenation of alcohols. Thank you.